Okay, so in this chapter, we're going to talk about the systems of, first of all, the differential equations, the real models, actually, real problems again in this whole chapter. But this time, we have two or more differential equations instead of just a single first-order differential equation. And these are, occurring in nature. Those kind of events happen in nature. So we're going to discuss several cases that model with systems of first-order differential equations. We're not going to solve those equations at this time. We cannot solve it at this point, actually, because when you solve these equations, you end up with higher-order differential equations, not the first order. Even though initially the equations are first order, when you try to solve it, it becomes higher order. Okay, so that will be the topic in the next chapter. So the first example is a radioactive series. Okay, so you have three elements, isotopes. So X, Y, and Z. And the series is X decays to Y and Y decays to Z with different half-time. Remember, half-time means the time it takes for the amount to decay to the half. Okay, all right. So there are two radioactive decays. In this case, X decays to Y and Y decays to Z. And they have different rate of decay. We call them number one, number two. So suppose that the decaying rate for X to Y is number one, the decaying rate for Y to Z is number two, all right? So in general, the number one, number two, they're different. And let X of T, Y of T, and Z of T denote the amounts of substances, X, Y, and Z, respectively, remaining at time T. So those are the amounts of isotopes at any moment. And then we can write down three first-order differential equations describing these events or series of events. All right. So from X to Y, we can write a dx over dt equals negative lambda 1x because it's decaying. So, the amount of X will decrease. So that's why you get the negative. So the rate of change of X is lambda 1. So we got the first differential equation that's familiar to us. Oh, okay. That's the same thing we had before when we have, one radioactive decay. But then we have another equation for the decaying or for the amount of Y. Okay, so remember Y decays to Z, but at the same time, it receives the decays from X, all right? So then the rate of change of Y will have two terms, one term from X and the other term, to Z. So the term from X will be positive. So that's lambda 1x. All right, and then it decays to Z, so that you have to subtract number 2y. Okay, right? So, this decays proportional to the amounts of the elements of X and Y, respectively. And then finally, we have another equation for Z. It just receives decays from Y, so it's positive. So that will be number 2Y. And again, the decaying rate is proportional to the Y itself. Okay. Does it make sense? Okay. So then there are 3 equations in this case, actually. And then, we can solve this, by substitutions, basically. But at this point, we just leave where it is. We're gonna solve it later in chapter 4. Any questions about this example? It's not an example, but it's an event. Okay. The second example is called the mixtures. Okay, so we already talked about the mixtures before. When we have a tank of a solution, you have some input flow and output flow. Remember? Then you can set up a first order different equation for the amount of the substance in the tank. dA over dt equals the inflow rate minus the outflow rate. Remember? All right. So in this example, now we're considering 2 tanks instead of just 1. We have 2 tanks, tank A and tank B. They're connected. So you still have input to tank A, but then you have an exchange between A and B. A and B are connected. Okay. So then you also have output at B. All right. So that's the situation. So we consider 2 tanks in figure 3.3.1 on page 107. So let me just try to find the chart, the diagram for this situation. I think it makes it a little easier to understand. In this case, if we have the pictures. So that's 3.3.1 page 107. All right, so page 107. So that's so if you look at this graph in here, so this is what we're talking about. Sorry about this. So we have 2 tanks, A and B. You see, there's the inflow to A and the exchange between A and B, and then it's outflow from B, right? And now you can see the outflow to A and the inflow to A and outflow from B have the same rate, 3 gallons per minute, to keep the solutions in the 2 tanks have constant volumes, right? 3 gallons per minute in, 3 gallons per minute out. So the volume of the solutions will not change in the two tanks. But at the same time, you have the flow from A to B with 4 gallons per minute, okay? And then from B to A, the flow is 1 gallon per minute. So then you get a 4 minus 1, 3 gallons per minute from A to B, and that's the net flow from A to B. So all of those flows, net flows, are 3 gallons per minute. So the solutions in A and B will have constant volumes in that way, right? Does it make sense? So, so let us suppose, for the sake of discussion, that tank A contains 50 gallons of water in which 25 pounds of salt is dissolved. So the volume of the solution in tank A is 50 gallons, and initially 25 pounds of salt is dissolved in this tank A. All right. So that gives us the initial condition, basically. And suppose that tank B contains 50 gallons of pure water. Okay, so initially, tank B also has 50 gallons, but there's pure water. Okay, both of them have 50 gallons in the volume. Okay, so that's also the initial condition. When you exchange between A and B, and your input and output, then the concentration will change both in tank A and tank B, right? Okay. So liquid is pumped into and out of tanks as indicated in the figure as we just discussed. The mixture exchanged between the two tanks and the liquid pumped out of tank B are assumed to be well stirred, okay? So, the mixture is, you mix solutions in each tank completely. We wish to construct a mathematical model that describes the number of pounds x1 of T and x2 of T of salt in tanks A and B respectively at time T. So we want to find a differential equation describing the amount of pure salt in each tank, just like we did in a single tank. That was a differential equation for the pure salt in the tank, right? So now we're trying to do the same thing for two tanks. Okay, so let's see how we do it. Let me just go back to this. Okay, so I guess the problem is very clear to us, right? So let's see how we can write down the equation. So obviously we have two tanks. They have different amounts of salts at any moment. So then we expect two equations, one for each. So let's just find the concentration of salt in each tank. Okay. So the concentration of salt solution in tank A is just x1 over 50. The volume of the solution in each tank is 50 gallons. Okay, in tank A, x1 is the pure salt, the amount of pure salt in tank A. So if we divide x1 by 50, the amount of pure salt by the volume of the solution, that gives you the concentration in tank A for the salt, right? Similarly, the concentration of salt solution in tank B is x2 over 50 because x2 is the amount of pure salt in tank B, and 50 is the volume. So amount of salt by the volume gives you the concentration. So the way to construct the equations is still the same. The rate of change of the pulsat in each tank is just equals inflow rate minus outflow rate. Okay. So for tank A, the rate of change of pulsat is dx1 over dt, and the inflow rate is what? Okay. Okay, let's see. The inflow rate. Okay, now, remember the pure water is pumped into tank A from outside. So that does not give you any pulsat. We don't have to worry about that. Okay, then we have a mixture between, interchange between A and B, but the input is from B to A, right? If we consider tank A, then there's only one input of pulsat. That's from B, and it's 1 gallon per minute. That's the flow rate. So if you multiply this flow rate by the concentration of B, that will give you the input, rate of pulsat from B to A, isn't it? Does it make sense? And similarly, the output rate for A is just from A to B. And the output rate is just the concentration of A times the flow rate from A to B, right? So we have to be careful about these two flows because from B to A and A to B are different in concentration and also the flow rate, right? So the equation for tank A will be dx1 over dt equals input rate from B to A. The flow rate is 1 gallon per minute. The concentration is from B, so you have to multiply the concentration of the solution or salt in B, which is x2 over 50, isn't it? And then the outflow rate from A to B, the flow rate is 4 gallons per minute from A to B. But you are flowing from A to B, so the concentration is from A, right? So that's the x1 over 50. That's the concentration in A. So then you just simplify this a little bit. You can cancel the gallon in each term. And you're going to get the negative 2 of 25x1 plus 1 over 50x2. So I just switch the two terms for the negative terms in the front. And I also canceled the 2 from 4 and 50. Good. So that's for tank A. Then you can do a similar thing for tank B. So now let's see what happens to a tank B. Okay, tank B. So the input is from A to B, right? So the input rate will be the flow rate 4 gallons per minute times the concentration of salt in tank A. And then there are 2 outflows from B. One is to A, one is to the outside. But the concentration for the flow out or outflow is the same, right? When you flow out from B, the concentration is the same. So you just add these 2 flow rates, 1 plus 3. So that's 4 gallons per minute outflowing from B times the concentration of solution in B, isn't it? So then we have two terms again. So the inflow is from A to B, so that's positive. And the flow rate is 4 gallons per minute. And the concentration is X1 of 50 again. That's because that's from A to B. So that's X1 of 50. That's a concentration in A. And the outflow, we have 2, 1 from B to A, 3 to outside. Add them together, that's 4, right? Gallons per minute. And the concentration is from B because the flow is from B, right? So that's X2 of 50. So just simplify these two terms again. You're going to get a 2 of 50, 2 of 25x1 minus 2 of 25x2. If you just cancel 2, from the numerator and the denominator in each term, right? So this, again, is system of linear differential equations in first order, but these two equations, they are mixed. X1 and X2 are mixed in the two equations. So again, when you try to solve it, it becomes second order in one variable. We have two variables, but they're mixed in the two equations. When you try to substitute, to solve it, it will become second order. Okay. Any questions?
So why wouldn't they both be 2 over 25 if you have 4 times x1 over 50 and you have 4 times x2 over 50 for both of them, right?
Are you talking about the second equation?
Yeah, the second equation, yes.
Yeah. Oh, yeah. Yeah, right. I'm sorry. Yeah. That's a typo. Yeah, I'm sorry. Yeah. It should be 2 over 25 x2 in the second term. Yes. I'm sorry. That's a typo. Yeah. Any other?
No, I was just looking at time.
Yeah. I forgot to change that to 25. Okay, so that's the problem of mixture of two tanks. No question, then we go to the next page. Okay, this time, we just talk about the population again. We have talked about population quite a bit, but we have never discussed when there are different species in the community ecosystem. You have different, animals, that will interact to each other. So then we can start from a predator-prey model. So like the fox and the rabbit, So in this ecosystem, you have a bunch of animals. You have plants. Okay. But when we consider both rabbits and foxes, for example, then you have to consider the fox take rabbits as food, right? Okay, so that would decrease the population of rabbits, isn't it? All right. So that's more realistic than before. When we just consider the natural growth and the death of the population. Okay, so we're considering two species, not just one species. Even when we consider the interaction that was between individuals within the same species. Now we have two species instead of one. So then we have two functions. or two variables, x and y. They are both functions of time. And x of t denote the fox population, and y of t denotes the rabbit population. Okay. So for fox without food supply, dx over dt equals -a times x. That's just the same as before. If it doesn't have, if there is no rabbit for the fox, then the population of the fox will decrease because of aging, right? They die, okay, because of aging. There's no food, so, right? But interactions between fox and rabbits, then you have the term of b times xy to add at the right-hand side to the equation, because foxes eat rabbits. Okay. And this term is proportional to the product of x and y, because the population, the increase of the population of foxes will be proportional to the population of both rabbits and foxes. Yes.
You're not there. I was going to ask something about d over dt.
Yeah, dx over dt is the rate of change of population for the fox. So that change becomes the aging negative ax. They have life. Okay, so that's because of aging. And the other term bxy is coming from the interaction between fox and the rabbit. When they eat the rabbit as food, and that will extend the life and also increase the population. Right? When they give birth, they have food, so the population will grow if they have the food from rabbits. Right? Okay. So that's for the fox. But for the rabbits, the situation is a little different. Rabbit eats grass. So that's unlimited food supply, vegetables or whatever you call it. So the change of population for the rabbits is just some constant d times y. Okay, that's positive. It's increasing because it just give birth. They have food, so they don't have to worry about the food. So the population will grow, isn't it? But when foxes are present, then the population of rabbits would decrease because of interactions between foxes and rabbits. They got eaten by foxes. So again, this term will be proportional to both x and y. Okay, the interaction, right? Okay. If you have more rabbits or more foxes, both will be good, or will contribute more to the decrease of the population, right? Okay, if you think about that. Okay, so then we have two equations to describe this ecosystem. So we just copy down the two equations, and that will give us two nonlinear differential equations in first order. Okay, they're nonlinear. You have term of x, y in each equation. So if you factor out the x on the right side of the first equation, then you get the dx over dt equals x times negative a plus by. And similarly, if you factor out the y from the right side of the second equation, you're going to get the y times d times cx. Okay, I forgot to put the y in here. Okay, on the right side, but once again, these are two non-linear differential equations. All right, and this model is called the Nocky-Waitera predator-prey model. So just to describe the situation of fox and rabbit or similar food chain. All right. So this time is even more complicated because the equations of of the system are non-linear for each of them, actually. So it's harder to solve. Any questions about this model? So you can see how we can use mathematical modeling in real life, even for the ecosystem. All right, so